Hello everyone. The subject of this talk is error resilience, which you should roughly think of as the amount of noise or errors a system is resilient to. The particular system that we shall be dealing with is the two-party binary interactive channel. I'll define this formally, and I'll show our new result, which states that there is a protocol on the two-party binary interactive channel that can tolerate a fraction of errors strictly larger than 1/8. I will explain in detail the significance of the fraction 1/8. But before that, let's start with some definitions. Okay, so let's start by defining the one-way binary channel. In this channel, there are two parties, Alice and Bob, and Alice has as input a message M of k bits that she wants to send to Bob. Now, this task is non-trivial because the channel connecting Alice and Bob is noisy. The noise in the channel is defined by parameter theta, which is such that if Alice sends some bits over the channel, then a theta fraction of those bits, an adversarially chosen theta fraction of those bits, can be corrupted before they reach Bob. In particular, if Alice were to send the message M to Bob, which is k bits, then Bob will receive a different message M prime, different from M in theta k locations. Okay, so how does Alice send M to Bob? Well, this problem is well studied and the solution is well known, which is to use error correcting codes. In order to send the message M to Bob, Alice first encodes the k-bit message into a longer code word C, say n bits, and then the code word C is sent over the channel. This code word C is corrupted in a theta fraction of locations to a code word C prime. But even though this is a corrupted code word, it still has enough information for Bob to recover the message M. Overall, the task of sending a message M over a noisy channel is the same as the task of finding an error correcting code C that allows decoding even after a theta fraction of its coordinates have been corrupted. So naturally, as the fraction theta of corruptions becomes larger and larger, the task of constructing error correcting codes becomes harder and harder. And it turns out that there's a sharp threshold, which is 1/4, below which there are error correcting codes that will allow Alice to send the message M to Bob, and above which there's nothing Alice can do so that Bob decodes M. Okay, so this is the one-way channel where Alice wants to send a message M to Bob, and the maximum error resilience that you can get is 1/4. Now let us jump to the two-way channel where both Alice and Bob have messages MA and MB, and they want to exchange these messages with one another. What this means is that after this protocol, Alice should know Bob's message MB, and Bob should know Alice's message MA. I will call this task the message exchange task, and I ask the same question. Suppose a theta fraction of all bits sent between Alice and Bob are adversarially corrupted. What is the largest theta for which Alice and Bob can solve the message exchange task? Or what is the error resilience of this message exchange task? Well, the first solution that comes to mind is to use the error correcting code that we have for the one-way task in both directions. Namely, Alice will take an error correcting code, encode MA using the error correcting code, and send the encoding to Bob. Bob can decode and get MA. Bob will use the same error correcting code on MB, send it to Alice, and she can decode and get MB. The task is complete. It turns out that this generalization of the one-way task gives an error resilience of 1/8. This number 1/8 is because this message exchange task is two-way. Alice needs to send the message to Bob, and Bob needs to send a message to Alice. And in order to fail the task, it is sufficient to corrupt one of the directions. Now, if the fraction of errors overall is less than 1/8, then in any of the two directions, the fraction of errors is less than 1/4. And we have error correcting codes that can decode from a 1/4 fraction of the errors. So we can use those codes to complete the task. Okay, so you can solve this message exchange task with an error resilience of 1/8. It turns out that this message exchange task is complete in the sense that even if Alice and Bob were asked to not output MA and MB, but some function of both the inputs, they can still do it by this protocol. Alice can send MA, Bob can send MB, and once they both know both the values, they can just evaluate this function on the values and get f of MA and B. So actually, what I described to you was a protocol that computes all functions f on MA and MB with an error resilience of 1/8. The bad thing about this protocol is even if the function is very simple, say the function when there's no noise, when theta is 0, requires only a small amount of bits to be exchanged between Alice and Bob. When there is noise, when theta is around 1/8, then Alice and Bob will need to send the entire input to one another before they can compute f. Is this blow up inherent? BR11 showed that no. BR11 showed that there is an interactive coding scheme, which means that for all functions f, there is a protocol that computes the function f and is resilient to a 1/8 fraction of errors. Moreover, this coding scheme for a function f has length only a constant factor more than the noiseless protocol for the function f. So the overhead of coding to a 1/8 fraction of noise is a constant. And the big open question after BR11 was whether this 1/8 fraction is tight. Namely, is 1/8 the best error resilience you can get from a two-party protocol? Or are there protocols that can get error resilience larger than 1/8? This number 1/8 is actually very interesting because 1/8 happens to be a natural barrier for protocols for the message exchange task or for general functions f over the two-party channel. I will describe this barrier, but before that, in our work, we actually solved this open problem, and we show that indeed there are protocols with error resilience better than 1/8. This is our main theorem, that there exists a binary interactive coding scheme. This is the same as the protocol in the sense that I just described, with error resilience 5/39, strictly larger than the barrier at 1/8. So as I said, we solve an open problem from BR11, and a lot of people have been working on this problem. This was mentioned in this EG816, it was mentioned in this survey, GL70, it was also mentioned in BE70, amongst other places. And we do that without losing out on the overhead. Just like BR11, our protocol only has a constant overhead for any function f. If the noiseless protocol computing the function f has some length, then our interactive coding scheme for that function f will have length only a constant factor more. So we have constant overhead. And with this work, because the best known upper bound on the error resilience is 1/6, we now know that the threshold for the two-party binary channel lies in the interval 5/39, which is due to this work, and 1/6, which is the best known upper bound. Okay, so this is our main result. And now for the next two sections, sections 3 and 4, I would like you to focus only on the message exchange task. Just to recall, this is a task where Alice has a message MA, Bob has MB, and they want to exchange these messages. Even though our scheme is more general, it will be worthwhile to just focus on the simple message exchange task for the next two sections. And finally, in section 5, I will generalize and go from message exchange to an interactive coding scheme for all functions. Okay, so let's start by explaining the barrier at 1/8. Why is 1/8 a barrier for protocols? And the reason is the following. You have this message exchange task where Alice has MA, Bob has MB, and they want to exchange these messages. And this message exchange task has 3 properties. And it turns out that each of these 3 properties corresponds to losing a factor of half in the error resilience. So the 1/8 number is actually achieved by half from binary alphabet, half from unique decoding, and half from the two-way task. Let's see why. So the first property I mentioned here is the binary alphabet. Namely, in our channel, Alice and Bob can only send bits to one another and not say symbols from a larger alphabet. Now, it is well known that if you have a binary alphabet, then the error resilience that you can get from error correcting codes is a factor of half lower than what you can get using, say, a large constant alphabet. And this factor of half is the first factor of half inside the 1/8. Because we use a binary channel, we can only get error resilience half of what we would have otherwise gotten. The second factor of half comes from the fact that we want unique decoding. This means that after the protocol, Alice and Bob must output MA and MB exactly. This should be seen in contrast with list decoding, where instead of outputting MA and MB exactly, Alice and Bob need to output a small list of values that is guaranteed to contain MA and MB, to contain their correct outputs. So instead of outputting the exact solution, they need to output sort of an approximation where they have a small set of values, one of which is the correct solution. Again, there are error correcting codes for the list decoding setting. And because it's a simpler setting, these error correcting codes have better guarantees. And turns out that the difference between unique decoding and list decoding is again a factor of 1/2. The error resilience that you can get for unique decoding is a factor of half lower than the error resilience you can get for list decoding. And this is the second 1/2 in our 1/8. Finally, as I explained before, message exchange, as I described, is a two-way task. Both parties need to output each other's messages. And this costs a factor of 1/2 in the error resilience because the adversary can only attack one of the two parties. And therefore, he only needs to corrupt 1/2 of the whole communication. So the factor is now lower by 1/2. And this corresponds to the third factor of 1/2 that we have in the 1/8 barrier. Okay, so you have these three properties that message exchange requires, each of which costs a factor of 1/2. But that does not mean you cannot combine these properties in a clever way to get something better. So it's not really a barrier in that sense. What makes 1/8 a real barrier is you actually cannot combine any two of these properties to get error resilience better than the trivial product. For example, if I want binary alphabet and unique decoding without the two-way task, so only the one-way setting, Alice wants to send a message to Bob. This is the setting that I just described, where you have the maximum error resilience theta equals 1/4, and is achieved, for example, by using error correcting codes. So you cannot combine the half from binary alphabet and the half from unique decoding to get better than 1/4. You also cannot combine the half from unique decoding and the half from two-way task to get better than 1/4. In this setting, you again have a two-way task. Both parties need to output. They need to output exactly, it's unique decoding, but they can use a large constant alphabet. And BR11 showed that for a general, which is the large constant alphabet, the maximum error resilience that you can get is again 1/4, which is just the half for unique decoding times the half for the two-way task, and you don't get any improvement. Finally, the third combination, which is binary alphabet, two-way task, but list decoding. Parties need to output a list of values, one of which is correct. And even for this setting, BE17 showed that 1/4 is the right answer. So you cannot combine the half from binary and the half from two-way to get something better than 1/4. And in this light, 1/8 is a real barrier. There are three properties, each of which costs 1/2, and you cannot get an improvement by combining two of these. And our protocol, which gets error resilience better than 1/8, actually shows that you can get an advantage by combining all three of them together. Even though you cannot get anything by combining these two, or these two, if you combine all three of them in the way our protocol does, you get error resilience 5/39, strictly larger than 1/8. Okay, so next I'm going to describe a protocol for this message exchange task. And the reason I chose this task is that for this task, our protocol takes a particularly simple form, and it's easy to describe it. Let's do that. Okay, so again, we have the message exchange task. Alice has MA, Bob has MB, and they want to exchange these messages. For this task, our protocol will have 39 n rounds divided into three phases. The first phase has 16 n rounds, the second phase has 20 n rounds, and the third phase has 3 n rounds. The total is 39 n. And an error resilience of 5/39 means that the adversary is allowed to corrupt at most 5 n of these 39 n rounds. Okay, so this is the structure, three phases, 16, 20, and 3. N here will be a constant factor larger than the length of the input, so our protocol has a constant overhead. And let's go straight ahead to the description of our protocol. In the first phase, Alice sends her input MA using a list decodable error correcting code to Bob. And this list decodable error correcting code, like I said, allows Bob to compute a small list of values. In this case, it will be a list of size 3 that will contain MA. So after this phase, we know that Bob has a list L. L has at most 3 elements, and one of them is MA. Okay, let's go to the second phase. In the second phase, Bob is talking to Alice. And in this phase, Bob sends MB, his original message, and the list L he computed in phase 1 using a standard unique decodable error correcting code to Alice. Now, the length of this phase is 20n. The errors are at most 5n. So the fraction of errors in this phase is 1/4. And there are error correcting codes, like I said, that will allow Alice to decode both MB and L from Bob's message in this phase. So we know that after this phase, Alice knows MB, so she can output it. Alice also knows L, the list Bob computed in phase 1. And this list L is guaranteed to have MA. Now, this list L has 3 elements, so it can have MA in position 1, in position 2, or position 3. And in the third phase, Alice sends this index or this position of MA in L, which is in 1, 2, 3, using an error correcting code, a special error correcting code that I will call small ECC. This small ECC is really interesting in the sense that it has a binary alphabet, so it's only made up of bits. It has unique decoding, so after this phase, Bob will know MA exactly, and it has error resilience larger than 1/4. Okay, so what happened here? I was saying all along that binary alphabets with unique decoding cannot give an error resilience larger than 1/4. What happened? Why does small ECC give that? The catch is that the code small ECC only has 4 code words, a constant number 4 of code words. And the fact that the code words are so small in number allows the code to have error resilience larger than 1/4. In this case, our code has an error resilience of 1/3, which means that the distance, the Hamming distance between any 2 code words is 2/3, or in this case, 2/3 of 12, which is 8. So here you can see that the Hamming distance between C1 and C2 is this first set of 4 values and the last set of 4 values, which is again 8, 2/3 of 12. Between C2 and C3, it's the first 2 sets, again 8. And between C0 and C1, we can do this for any pair, but let's say for C0 and C1, it's again the first set of values, which is again 2/3. Okay, so we use these code words in our protocol to get better error resilience. I chose to not describe the analysis of this protocol and how we get 5/39, but instead, I will end this section by saying how we bypass the barriers that I described for the 1/8. So let's recall the 3 barriers were: 1, binary alphabet does not have codes with distance better than 1/4. 2, unique decoding costs a factor of half. And 3, a 2-way task should naturally cause you to lose a half in the error resilience. Let's see how we get around these. Well, in the first phase, we use a list decodable error correcting code. And this is where we get around the unique decoding barrier. Because we use the list decoding code, we do not have to lose the half that we have to lose for list decoding. In the second phase, Bob sends the list L to Alice. And note that this is only possible because the task is 2-way. If the task was 1-way, if Bob wasn't speaking, then there is no way Alice could know L, which is a function of the noise injected by the channel. The fact that the task is 2-way allows Alice to know L. And it is here that we get around the barrier that it's a 2-way task, because we actually rely on the fact that it's a 2-way task. In the third phase, we use powerful binary codes with a small number of code words. Again, these are codes that are binary and unique decodable, but do not lose the factor of half. They have an error resilience of larger than 1/4, 1/3 in our case. And we get around these 3 problems in 3 different ways, but we are able to combine all of them in our protocol. The list decoding works with the interaction because you need to send a small list. The list also must be small because you can only send, this code has few code words, so you can only send a small number of indices in third phase, so you can use powerful binary codes. And combining all 3 gives an error resilience of larger than 1/8, as claimed. Okay, so this was our description for our protocol for the message exchange task. And in this last section, I will go from this protocol for the message exchange task to an interactive coding scheme for all functions with only a constant overhead. So let's do that. Here again is a sketch of our coding scheme. You have phase 1 where you do the list decoding, phase 2 where you send the list, phase 3 where you use the small error correcting codes. And let us imagine running this scheme for a general function where Alice and Bob must interact. The first problem that we face is in the first phase itself. Here, when Alice was sending a message M to Bob, we have a list decodable error correcting code that will allow Bob to get a list of size 3 that contains MA. But for general interactive tasks, we do not have any such interactive list decoding scheme. We do not know a list decoding scheme that, after Alice and Bob both talk, will allow them to have a small list of values with the third value in the list for general functions. And the first step that we do in our proof for general functions is to design such a list decoding scheme. We design a scheme with error resilience matching the one-way scheme, so we do not lose in the 5/39. But it is for all interactive tasks. And after this, we can guarantee that Bob has a small list of values with the correct answer. But this also causes another problem. And the problem is now that Alice and Bob are interacting in phase 1 is longer. Both of them are talking in phase 1, it has to be longer. This means that phase 2 must be shorter because the total length of the protocol is the same. Now, if phase 2 is shorter, the adversary can now attack this phase and make sure that when Bob is trying to send his list L to Alice, Alice does not receive L correctly. Why was receiving L important? Well, receiving L was important because Alice wants to, in phase 3, send the index of MA in L. And she can't do this unless she knows L exactly. And if the adversary now, because the phase is shorter, attacks this phase and makes Alice be confused about L in phase 2, he also renders phase 3 useless. And therefore, this is a new attack that we need to now deal with. How do we deal with this? Well, it turns out it is not clear why, and I'm not being exact when I'm saying this, but still roughly it turns out that after a lot of effort, we can make this protocol have the property that, yes, the adversary can attack phase 2, but Alice can find out whether this happened or not. This is actually really delicate. In general, when an adversary corrupts a message, the parties do not know that the message was corrupted. But here we design these phases in a manner so that if the adversary attacks this phase, if a lot of interruptions are in phase 2, then Alice can detect this. And when Alice detects this in phase 3, she just sends a code word saying that phase 2 was corrupted. I did not get a lot of information. Again, this can be done because our small code that I described at 4 code words, but we only used 3. P was in 1 to 3. And for this, we use the 4th code word to say that the list that I received in phase 2 was wrong. Okay, but this does not really solve the problem because now phase 3, if the list in phase 2 was wrong, in phase 3, Bob does not know what was the right index. And the way we have Bob output the correct value despite not knowing the right index is making sure that if the adversary attacks the second phase, then it must spend a lot of errors in the second phase, which means it must spend relatively fewer errors in the first phase. And we make sure that these fewer errors are such that our interactive list decoding scheme would actually reduce to a unique decoding scheme for these small number of errors. So again, in general, our scheme is interactive list decoding. It outputs a list of size 3. But if the adversary attacks the second phase, Alice will say that it was attacked in the third phase. Bob will decode this. And this can only happen when there were a lot of errors. And when this happens, Bob will just take this scheme to be a unique decoding scheme and output the correct answer based on this phase. I'm not sure if the last 30 seconds of what I was saying made sense, but overall, the structure is that we build on the same sketch on message exchange. We replace the list decoding with the interactive list decoding. This causes a problem in the second phase where the adversary can now attack this. But we rectify this problem by using the fourth code word that we didn't use for message exchange and ensuring that whenever this attack happens, the first phase itself is sufficient for Bob to output the correct answer. Moreover, we also ensure that the list L can be corrupted in phase 2, but together phase 1 and phase 2 give Alice enough information so that she can always decode MB correctly. She can attack phase 2, yes, but regardless, she will always be able to decode MB correctly, and only the list L may be attacked. Okay, so this completes the description of our general interactive coding scheme. And I would also thank you for listening and conclude my talk. Thanks.